Okay, good morning, everyone. Okay, if I was allowed, I'd play a Star Wars soundtrack here for this lecture, but then they would delist it from Berkeley YouTube, so I can't. But today we're going to talk about superposition and equivalence, and I kind of dubbed this circuit Jedi techniques because, as you'll see pretty soon, these allow you to really easily see through the circuit complexity and understand kind of what is really going on in circuits that are pretty complex, as we'll kind of keep building up through the rest of the course. And the real goal here in doing this is really to enable us to design interesting systems. And to design interesting systems, we need to have insight. We need to understand how the blocks talk to each other, how they communicate, etc. And if you're just always tasked with solving a huge linear system of equations, you really have no understanding what's actually going on inside. And so these techniques we're going to do today will help you. They're very necessary tools to help you understand what's actually going on and how to go about building systems from scratch. So the goal is we want to design interesting systems. So we need the tools that provide insight. Okay, and that's what we're going to do today. Before I dive in, there's a quick announcement on the midterm regrade requests are going to be accepted by Saturday night. So I think that was posted as well, but just keep that in mind. So you're not late in reviewing the midterm, what you did, and submitting. See how it was graded, submit the regrade request if you think something was off. Okay, so a quick reminder is, let's look at the circuit analysis objective. Right. So that was to find some set of unknowns in the circuit, and then we said this was like the currents of the elements, and then node potentials, right? Okay. If you have these, you know everything about that circuit, right? So that's usually what we did in circuit analysis. And that was for some circuit matrix A and some stimulus vector B. And that B was essentially a bunch of independent sources, IS1 through ISL, and I'll just label this like VS1 through, let's say, VS. Dimensions have to add up, so it's K minus L. Okay. These are all independent sources. And we'll clarify this in a bit, but just for now, everything that we've done so far, both elements that we've defined, the voltage source and the current source, they're independent sources. Their values are set. They're basically batteries, right? We'll see later there are some other devices that will incorporate into the whole thing. They're not independent. But for now, let's just stick with this. So this formulation allowed us to formulate, through a painful seven-step procedure, formulate this type of system of equation, right? AX equals B, you go through the procedure, it's tedious, but you can always do this, right? And because we followed the procedure and we've labeled our reference node, we've eliminated all our rows of A are linearly independent, we know that there is an inverse. We can solve this uniquely, right? And so we can write that x equals a minus 1 times b. So this was our solution. Right. But actually, let's take a look at a little bit inside that solution. What does that really mean? Right? It's some matrix multiplying a vector, but what's really going on? Right? That's what we want to try to find out as circuit designers. So let me pick one of the elements in X. Let's say some current, II, right? That's essentially just the ith variable in this unknown vector, right? Some element I has a current II, right? So if I follow this matrix vector multiplication, that's just one row of A inverse times the full column of B, right? So let's see what that is. We'll just write it out as, I'll just write it as alpha 1 is1 plus alpha L isL plus blah, 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 alpha M plus K times Vs M plus K minus L. Right. So II is just a linear combination of all the sources in the circuit. Right? That's really what that matrix vector multiply means. That the variable that I'm looking for is a linear combination of the sources in the circuit. So each source contributes to this variable through some coefficient. Right? So we call that coefficient a response to that source, right? So if I'm interested in a certain variable, voltage, or potential, or current, each of the sources in the circuit contributes something, right, to that variable. So, and as you see, these coefficients are completely independent of all the other sources. They're just some values, right? They're determined by other circuit components, let's say resistances, and these kinds of things, right? So they represent kind of individual responses to each one of the sources. So same deal with, the supply. So that's some beta 1, is1 plus blah, 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 plus beta M plus K. Yes. Right, same deal. So these are both linear combinations of sources. Right? So, that's true. Then I can start looking into these individual contributions separately. So how do I do that? Well, let's say I can represent II as I1 plus blah, 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 plus IL plus M plus K, where each one of these is, let's say this one is alpha 1 is1. This one over here is alpha L isL. This one is alpha M plus K Vs plus K minus L. Right? How do I find each one of these components separately? Is there a way? Yes? Yeah, mathematically. So the comment was, you look at this expression. If I'm interested in this component, I will just set all the other sources to 0. Mathematically, it works out. Right? These are independent sources. I can control their values. Right? And I just set them to 0. I solve, again, the whole circuit. Right? If I set them to 0, I still need to, if I know A inverse, okay, I've already solved the circuit, so I just multiply out, right? But sometimes this mathematical operation of zeroing a source, as we will see, will make my circuit solve very simple. So I don't even maybe need to go and find this giant inverse in the first place, which is kind of what we're going to be doing. But just mathematically, if I solved and I plugged in zeros here, I would be getting these individual components when I do the multiply out. Does that make sense? Yes?
What's the subscripts
On the V, this is just VS1, VS, and just to make the dimensions work, M plus K minus L. Not visible? Yeah. VS, M plus K minus L. Yeah. Okay, does this zeroing make sense? Mathematically, right? Okay, so essentially we can calculate II separately. By nulling the other sources. Okay, so I think the question is, what does it really mean to null a source? Like, we know mathematically what it means. In this expression, I'll just put a 0, right? Like where ISL is, or where this VS is, where actually everything is except, let's say, IS1, if I want to find II1. But really, in the circuit, what does it mean? Let's take an example, right? Let's do a voltage source. Right. So, how does the IV curve look like for a voltage source? Yeah, vertical line at Vs, right? So let's say it's Vs here. So, if I say that Vs equals 0, which means that's what I want. I want to null that source. I want to assign it a value of 0. How does the IV curve look like then? Is it still vertical? Okay, where? Okay, yeah. So it basically moves to here, right? So what element does this become? A wire, right? So it becomes a wire. This is just, we're recalling a definition of a wire, right? In its IV, a wire has voltage of 0 across it and can pass any current, right? So these two are identical. And remember, any element is only defined by its IV function, right? That's the only definition of the element. So I'm not really cheating you when I say that voltage source of value 0 is exactly the same as a wire, right? They have identical IV characteristics, right? So therefore they are equivalent. Does it make sense? They're equivalent from the standpoint of circuit analysis. Voltage source, of course, has some chemistry in it and whatever, and I'm just pretending I'm assigning a value of 0. If the voltage source has a value of 0, it behaves as a wire. Does that make sense? Okay, let's do the current source. Okay. Okay, what does the current source look like in IV space? Horizontal, where? At which value? Yeah. Okay, IS. And now, when we do IS equals 0, just shifts down, right? So, right, shifts down to this. Well, what element does that correspond to? Someone in the back? Open circuit, right? Okay. It's an open circuit. And again, for open circuit, we had an IV. And this is the line. Right? So again, IV is identical. The two elements are equivalent. Right? So, what goodness does this bring to us when we try to do circuit analysis? Starting to get an idea? Any ideas? Yes?
You can replace all the voltage sources except for one with wires. All the current sources with like open circuits and then solve them for specific components of the system. Like you had to do for every other element.
Yeah, so the comment was, hey, I just come in, all the voltage sources that I'm looking to null, I'll replace with a wire. All the current sources I'm looking to null, I'll replace with an open circuit. A wire was already a very simple thing for us, right? There's a wire between the two nodes, we know it's the same potential. If there's an open, we know there's zero current. We don't even need to calculate it, right? So it significantly simplifies our circuit. And we'll see shortly, I mean really significantly. Like out of n sources, you now have only one, and a bunch of branches are gone or shorted, right? And circuit becomes easy peasy. Yeah. So, and that's what we're going to be doing. So you're going to be able to see really quickly what's happening with the circuits once you do this. Okay. So in fact, let's just do an example. Just get the paper. So, we're going to do an example, but before that, I want to sort of formalize this. So let's call this superposition. Okay, you're not seeing this. Okay. So, we're going to find I's and V's, or U's, by turning independent sources on one at a time and solving the circuit. Okay, makes sense. So let's do an example. This example is called a voltage summer. In fact, a bunch of circuits that we're going to do have some function. They're not just there for you to get busy and solve them. They actually do something. And so remember these functions just like the voltage divider, right? It had a function, and then we later used that function to create a whole touch screen. Just one simple circuit function, right? So now we're going to be learning, it's kind of a signal processing with circuits, right? Each mathematical operator will have some circuit pattern or some circuit block associated with it, and we're just going to learn a whole bunch of those. And then you know the language of circuits, the mathematical language of circuits, and you can go compose these functions. Right? So this one is voltage summer. So let's see how that works. So typical thing, I'll label my reference node. I'll label the one remaining node in the circuit. That's unknown. Right? And because I said this is a circuit that produces some function, right? Functions normally have input and output, right? So in this case, these inputs are these two sources. So, and the summer is supposed to produce a sum, some weighted sum of these current voltage source values. So I'm going to measure that value as V out, right? Between this potential U1 and 0, right? That's where I'm measuring that mathematical operation. Okay. So something we can write really quickly that you already know, U1 minus 0 is V out, right? There's just a voltage definition. So U1 is really V out in this case. Right? So let's do our superposition, right? Step 1, we're going to say compute our response to VS1. Remember, in each step, we compute a response to one source that is on. Everything else is off, right? So that means, in this circuit, because there's only two sources, that means we need to set VS2 to 0. Right? So, in these steps, we're going to be redrawing the circuit with this nulling to see how it gets simpler, right? And maybe we don't even need to do any analysis. We already see the answer, right? So let's see this one. So let's say this is VS1, R1, R2, 0. And now I'm going to just draw. Let's draw it a little bit more. I'm drawing this red line, which is a wire, in the place where VS2 used to be. Why did I do that? Yes. Yes, because we said VS2, we're setting it to 0, and we know that when we do that, the voltage source becomes a wire, right? So that's what we did. Okay. So, does anyone know? Okay, so actually, let's label this. This I cannot no longer label U1, right? Because this is not a complete circuit. So this is just one component, remember, of what we were doing, right? This would be, so for example, this would be UJ1, right? So if I now all the other sources, I'm only computing the response to one of the sources. So that's one of the components of the final value, right? So I'm going to label this U11, right? And correspondingly, this output, I'm going to label Vout, 1. Because that's only a portion that corresponds to this source, VS1. Does that make sense? Okay. So, who can tell me right off the bat, like what this is, what this value is? Just not even do a single equation. Yeah. R2 over R1 plus R2 times VS1. Okay, so how did you do this? Some magic trick? Jedi trick. Okay, but tell me, please. Voltage divider, that's right. Okay. Happy face. This is really what I'm talking about, right? We didn't have to write a single circuit equation. We know this circuit already, right? So just by simplifying it, we already see what it is. Okay, so let's see if you know this one. So we're going to now compute our response to VS2, set VS1 to 0. Right? So that means I have R1, I have R2, I have VS2, 0, and then I have a wire on this side. And, of course, this is now U1, 2, and this is V out 2. Okay. Now, maybe take 30 seconds, talk to your neighbor. Tell me, and after that I want to know what is V out, 2. Okay, any ideas? Yes. Okay, so R1 over R1 plus R2 times VS2, right? Yes, VS2. Woohoo! Okay, so what is this circuit? Voltage divider. That's right. Okay, another smiley face. Really happy this time. You know, this is kind of like, looks a little bit weird, but if you look at it, you know, it still is a voltage divider. It's just a symmetric mirror image of this one on top. So now that I have these two components, V out 1 and V out 2, I can now assemble my final value. V out is now V out 1 plus V out 2. Yes? Okay, I was waiting for that question. So look at it here, right? V out is the difference of two potentials in the circuit, right? So, and because the other one is the reference, it's really just U1, right? So this is the same thing. So this is equal to U1. This is equal to U1, 1. And this is equal to U1, 2. Right? And we said that any voltage, let's say U1, in the circuit is a linear combination of responses to all the sources. In this case, we only have two voltage sources. Right? So let's say if this was VS2, then this whole element will be U1, 2. Right? And then another element here would be U1, 1. And then this would be U1. Right? Okay. So we can do this, and let's now sum it up. So it's R2 over R1 plus R2 VS1 plus R1 over R1 plus R2 VS2. And, you know, we can call this like alpha and this some beta. This is less than 1. This is less than 1 in our case. So this is just a property of this summer. Right? It's useful when you see these blocks to kind of remember what the properties of these blocks are. Right? So one is that, so if I told you, hey, build me a summing circuit, Okay, you go like, boom, this is a summing circuit. And if I didn't specify anything else, that would be sufficient, right? This is a very special summing circuit because, as you see, the coefficients with which I'm summing are less than 1. Right? So if I told you, build me a summing circuit where coefficients are greater than 1, then this is not that circuit, right? So you need to add something else. As we'll see later, we're going to be building up more complex things. There's another important thing about this one, is that the coefficients are not independent. Right? I cannot separately set this alpha from this beta. I would set alpha by picking the resistor values, right? But the moment I pick R1 and R2, I've already set beta, right? There are other summers where you can independently set these things. We're going to do some, neural network examples later. People try to build them out of these summers, like artificial neurons. And again, setting the weights the right way is very important. And being able to set the weights independently is important. So this is not one of those. Yes?
How do you know if the coefficients are less than 1?
How do I know if they're less than 1? Well, because resistor values are positive, right? So it's at least, if one is like infinite and another one is a 0, then it's a 1, right? But these are finite resistor values. Okay. So, try to do some new technique. This is basically it for superposition. We're going to use it, but it's very, yes?
So in that equation, are we assuming all the coefficients for the currents are 0?
In which equation?
So for V out, since like from our earlier equation, we had coefficients for all the currents and coefficients for...
Oh yeah, great question. Are we assuming that all the current coefficients are 0? Well, are there any currents in this circuit? Current sources in this circuit? No. So all the coefficients related to the response to current sources are 0. Or in fact, because there's none, even the values of the current sources are 0, right? Because they don't exist. When the value of current source is 0, it's just an open circuit, right? I could attach to this, let's say, like some open circuit, nothing's going to change, right? Does that make sense? Yeah. Yes?
What is a current source? If we're talking about like a real example.
Oh, this is an awesome question. It's really a good question. And you'll actually see in the building a current source is super hard. It's not a battery. It's not a voltage source. In fact, how we're going to do the touch lab, you are going to build first only a part of it because you don't yet know how to build a current source. So you're going to build just a sensor and then simulate a current source. And then when I show you the op-amps, then you'll be able to go and build a current source out of the voltage source. All right. So otherwise, just building a current source itself, something that constantly pushes electrons, charge, regardless of the voltage, is actually, like through some chemical or physical reaction, it's actually super difficult. Yeah?
The fact that alpha and beta in this example add to 1, say anything about the...
It's a property of the circuit, right? Yeah, it's a property of the circuit, but really, that's something to keep in mind. Yeah. Okay, let's move on. So we're going to do the next technique in our JEDI tool set, and you'll see they're a little bit related as well. So if I have circuit 1, and that circuit 1 talks to circuit 2 through, let's say, 2 connections, right? There's 2 terminals. All that these circuits care about is what is this current, I out 1, and what is this voltage, V out 1, between them. if I put some other circuit here, and it produces the same values of current and voltage, this I out 1 and V out 1, when attached to this circuit, then these two circuits are equivalent. So, in other words, if I put up something like this, this is V out, I out 1, V out 1. So, when I add some other circuit, circuit 3, as long as I out 1 and V out 1 are identical to the ones above, circuit 2 has no idea that I've changed anything. To circuit 2, these two circuits, 1 and 3, are equivalent. Yes?
What about the bottom wire?
Current through the bottom wire. Oh, great question. Question is, what's the current through the bottom wire? Well, the answer is in KCL. Right? If I treat this whole circuit as one big element, it has two terminals. The current coming in has to be the current coming out. Right? Otherwise, there will be some accumulation of charge in that element that's indefinite, right? So something is going to blow up. Does it make sense? Like, by KCL, current into any element has to come out. Into any junction has to come out, right? Okay, so the point is that these circuits know each other only through these two variables, the current and the voltage. And if I can guarantee the same values, I can create a bunch of equivalent circuits that are simpler to analyze and work with. For example, let's say you work really, really hard when you go out and do build, in industry, you build circuit 1, right? And then you want it attached to circuit 2. So you build circuit 1, you don't know what circuit 2 is. You just have been given some specifications that it has to work with circuit 2. So you build circuit 1. You hook it up, it works with circuit 2, you get these values. Everything's great. Now, you go in and you want to make some small modification to your circuit 3, from circuit 1 to circuit 3, but you don't really want to go and hook it up to circuit 2 again, solve the whole big thing. You would want to be able to have a very simple representation of circuit 2 as you're working on circuit 3. Or vice versa, you're building this and you don't know what you're going to load it with. Whoever you give a model of your circuit that you're building, you need to give them something simple so they can always check what the answers are going to be when they attach different things. Right? Think about like when we did the resistive touch. We were measuring the voltage at the end, but what if I added a resistor? Right? So what if this circuit 2, I compute this with no circuit 2, and then if I add a resistor as circuit 2, I again need to compute all these values, the whole 7-step procedure, big matrices. I add another resistor or a current source in circuit 2. I again need to compute everything from scratch. Right? It's a very tedious procedure. And it also doesn't really tell me how this circuit 2 affects my circuit. Right? So what we're going to do here is we're going to create equivalent, simpler circuits. They're essentially models of how our big complex circuit behaves. Models that produce the same IV as our circuit for any IV condition in that plane. So what I'm trying to say is that every circuit has some I out, V out 1 behavior, right? It could be this, it could be that, it could be this, etc. In fact, one circuit, for example, very simple circuit like this red, what would that be? A resistor, right? So 1 over R. One circuit like this, what would that be? Current source. One circuit like this. Voltage source. Okay. One circuit like this. What is that? Yeah, it's a combination of a circuit of a current source and a resistor, right? So things like that. I can, by combining resistors with sources, I can create various slopes and various offsets, right? And so whatever is inside here, if I have a resistor and a source, I should be able to model that behavior. Yeah. Oh, you're just stretching. Okay, good. So in circuits, two elements are equivalent if they have the same IV characteristics. Right. And given that we're doing linear circuits, meaning every single one of these curves is a line, right? How many parameters do I need to emulate this line, to be able to represent this line? 2, right? So 2 points will define a line. An offset and a slope would define a line, right? And we just showed here that a source provides offset and a slope is provided by a resistor, right? So let's have an example. So let's say this is a source. And what I'm doing here, I say, okay, I treat this whole combination as an element. It is a circuit. It's not just a simple circuit element. It's a complex circuit element. But nevertheless, it has I element and has V element. And I can now draw the IV space for that, right? In other words, I'm boxing this to be like one element, right? Okay, so why don't you talk to your neighbors, figure out what is this IV curve? Anyone come up with the equation yet? No? Okay. Anyone? Equation? No? Okay. We'll derive it, but just intuitively, how do you think this IV curve looks like? I'm seeing something like this, right? So like a sloped, there's a line with some slope. And does it have anything else? Does it go through origin? No. Somewhere. It's offset somewhere. Okay, that's good enough. So let's take a look at what equations can we write here. It's just circuit analysis, right? So since I already have this V element that's given, right, I'm just going to write like a little KVL around this, right? So I can go and say that V element is equal to Vs plus Vr. And Vr I'm going to label as this, Vr. The reason why I labeled plus and minus here is because the current I element is going into R, so I want to use that as a passive sign convention, right? So that is Vs plus I element times R. So this is V element. Does that make sense? Okay. So from here, I actually wanted I element as a function of V element. So that's 1 over R times V element minus Vs over R. Right? So let's draw that curve. Does this make sense, what I did? Everyone clear on this equation? Okay. So that's a line like this where the y-intersect is minus Vs over R. Right? That's when V element is 0, I only get minus Vs over R. And then this point over here is what? What's the value of this point over here when I element equals 0? Vs. How could I have gotten that even without solving any of this? Yes?
Could have seen that there was a voltage source and start at that value Vs and then draw the slope of the curve.
Okay, yeah, I could have done that, like just seen the voltage source and drawn the slope. I need to kind of, this first sentence that you said, when I element, notice that this point here is when I element equals 0, right? When I element equals 0, I know there's an open circuit here. Right? So if I element equals 0, there is no voltage across R, right? We did that for the touchscreen, right? There's no current flowing through a resistor, there's no voltage across it. Therefore, V element equals Vs. This is the same exact situation we had in the touch, right? Where U mid, we could measure U mid somewhere else because there was no, even though resistor was in between U mid and the end potential, simply because there was no current, right? So this is exactly the same thing. When I element equals 0, the output is Vs. And then we know that the slope is R, so yes, 1 over R, so then we can just draw that. Another interesting thing is that when V element is 0, which means that this is a wire, right, then I element is minus Vs over R. That's just Ohm's law, right? And so I get that point for free, right? So with these 2 points, I can draw a line. That's another way to solve it without even writing any of these equations. Okay, so just more general. Let me just grab some paper. Let's generalize this a little bit. So if we have a circuit and it has I element, V element, I can always represent the behavior of this with a circuit that has 2 degrees of freedom, meaning 2 parameters. One is the voltage source, and another one is a resistor. Right, and this is called, okay, you see it, Thevenin equivalent. So this is I element, and this is V element. So, essentially, we need a min of 2 elements a resistor and a source to create any IV line. Now notice, the emphasis is on line, right? Because we just saw earlier that any circuit we have will, if I'm just looking at I element, V element, it will always be a line. Right? Because we know that our circuits only have sources and resistors. There's nothing else. Right? So IV is always going to be a line, and to represent a line, I need two parameters. So if I have a resistor and a source, I can do this. Now, one of the ways to do it is this Thevenin equivalent, where I have a voltage source and a resistor. Another way is Norton equivalent, and that one uses a current source. R Norton. Again, same thing, I element. Okay, we're going to analyze the Thevenin first, but, oops, sorry. This is not here. Okay, I'm going to draw it in red so people remember. It's actually here. Okay. How could I figure out so quickly, okay, if I'm not looking at my notes, that what I did made no sense? Tie the resistor in series with a current source. Yes? So the resistor would still have the same current, right? But would that change anything in the circuit? Yeah. So the resistor is basically useless, right? It just doesn't do anything, right? And so I only have 1 degree of freedom. I need 2. And to have 2, I need to tie it in parallel. Okay, great. Thanks. Okay. So let's check what the curve looks like. We kind of already did this example, right? So I'm just going to... We looked at this circuit, right? It's basically this circuit, right? I just had different values here, but we've already analyzed it. So let's just copy the values. This was minus V Thevenin, so the curve looks like this. This voltage is minus V Thevenin over R Thevenin. This voltage here is V Thevenin. And the slope here is 1 over R Thevenin. Right. However, this actually tells us how do we find these values. Right? If I look at this IV curve, we just said that I can find V Thevenin as the output of the circuit when I element is 0. Right? Just looking at this circuit, V element is equal to V Thevenin when I element is 0. Right? That means there's no voltage drop on R Thevenin. So the same thing has to be equivalent for my circuit. So to find V Thevenin, we're going to connect an open circuit across 2 terminals and measure the open circuit. And that will be our V Thevenin. Does that make sense? Yeah. We just don't want to let any current going through that measurement, because then there will be some voltage drop on this R Thevenin equivalent, so we're not reading out the V Thevenin. Okay. Then the second thing is to find R Thevenin. If you look at this circuit, to find R Thevenin, I need to zero out this voltage source. If I zero out this voltage source, then this element is going to become R Thevenin. Right? So to find R Thevenin, we're going to zero out independent sources. Basically, we're finding a slope. This slope. So there are two methods for doing this. Okay? And as we'll see shortly, once you get a little practice, for some topologies in circuits, one method is easier, and for the others, the other method is easier. So this is a circuit with zeroed sources. Right? And what I'm going to attach to this circuit in one case is a test voltage, and I'm going to measure current. And then my R Thevenin is going to be equal to V test over I test. In another way, so or, we again have the same circuit. And in this case, I'm applying a current source, I test, and I'm measuring V test. Again, when I measure V test, I apply the same formula, R Thevenin equals V test over I test. So this is just a procedure, right? The reason why I'm zeroing the sources, hopefully, is clear. I want to get rid of this source, right? To only see the slope, the R Thevenin, right? So I'm nulling the source. Similarly, if I did it for the Norton circuit, if I null the source, it becomes an open, right? So again, the only thing that remains is R Norton. So from that, you could kind of already guess what's the link between R Norton and R Thevenin. If these two things represent the same circuit. Do you see the link? Maybe 30 seconds, talk to your neighbors. If these two circuits are equivalent, what's the link between R Norton and R Thevenin? Okay, any ideas? Yes. They are the same. So, R Thevenin equals R Norton. Right? I mean, simply looking at it, when I null this source, it shorts, right? It creates a wire here. So, this thing becomes just R Thevenin, right? When I null this source, it just becomes an open, right? So there's no current going there anymore, doesn't exist anymore. So the only thing that remains is R Norton, and these two are supposed to be the same. So I have R Thevenin here and R Norton here. The only way for them to be equivalent circuits is these two values are exactly the same, right? So R Thevenin equals R Norton. And then another thing you can see from this is that if I make V element 0, which is this point over here, right, then my I element is minus VTH over RTH. Right? Well, if in this circuit I make V element 0, means I'm drawing a wire here across. Right? Then, what is I element in that case? If I draw a wire here, what is I element for this circuit? Well, it is, it's minus IN, right? Because IN flows this way. This is the arrow. And I element is marked this way. But yeah, no current goes through RNO because there's 0 voltage across it. So all of this current flows like this. So then, that means that this is equal to minus INO. So that's the connection between the two. Okay? We're going to hash this out a little bit more, but I want to just give you a little bit of a kind of insight. So, before we move on with this procedure of zeroing out the sources and finding actually our Thevenins in examples, I so far mentioned several times that when we're zeroing stuff, whether it's for superposition or now for the equivalence, we are only zeroing out the independent sources. So I want to give you a few definitions for the dependent sources that we're going to be seeing in some devices and actually some circuits that you're going to analyze, just so you have them and you know how to apply the math. Essentially, one example is, let's say, a transistor. You have millions of transistors, billions in your pockets, in chips. We can model them as voltage-dependent current sources. And so once you have that model, you can analyze these circuits very easily. And so I'm going to show you a few of these definitions. Dependent sources. So if you have a control voltage, that voltage controls this source. So this is then called voltage-controlled voltage source, or VCVS for short. Right. Then we have, again, control voltage, but now we control the current source. I'm drawing them as diamonds because that tells you that it's not independent. There is some variable in the circuit, some voltage or some current that controls it. Right. So I'm going to label this as GVI. Alpha here is unitless because this is also a voltage source. This G has 1 over ohm type unit. So this is voltage controlled current source. VCCS. And then we have IJ, alpha IJ. So this is current controlled current source. And any guess? We're saving the best for last. Okay. This is R times IJ. So this is current controlled voltage source. Right. So when we do op amps, for example, this is going to be our model. Yes? It represents some device, right? In some case, it represents a very big device, very complex circuit block, which is like an op amp, a bunch of transistors in it, right? So, for example, we will see we can represent it like this, right? Or, in some cases, it represents just a component, like a transistor, in which case, something like this, And you'll have it, I think, on discussion or homework. So it's just but for you, it's just a model in a circuit, and you can apply KVL, KCL, 7-step procedure, the magic quick procedure that I did last time. All of these analysis apply. You can apply superposition. Now, of course, in superposition, you cannot null this source because this is a dependent source. In equivalence, you cannot null this source. It's a dependent source, right? So just keep that in mind. This is why I defined them, so we can know about them and then do things appropriately. Okay. So let's jump to an example. Now we're going to do here simpler examples. We're not going to do these dependent sources. These we're going to do in discussions a little bit. So here is a very simple circuit. Right. And again, this is some box. Right? This is some circuit that has 2 resistors in it. And I want to find an equivalent circuit. Right? I want to find a circuit that's a Thevenin circuit. Okay, step 1. Step 1, I just attach an open circuit to this, and I measure the open circuit. So I'm just going to redraw it for clarity, but that's really what it is. So this is it, and this is the open circuit. So what is the open circuit in this case? What's the voltage between these 2 points? 0. There's no source, right? Okay, so that means V Thevenin equals 0. Okay, step 2 is a little bit trickier. So no sources. So we have no sources already. We have nothing to null out. And then we apply test current. Okay. Now, I already made a choice what I'm doing, right? I said I can either apply a test current and measure the voltage or vice versa, right? But I already chose to drive it with test current. And there is actually a good reason why. I want to make my life easier to compute the v-test. Driving with I-test is because I see these 2 elements in series. Right? So we're going to clarify that in a moment. But just keep that in mind. So can anyone tell me what v-test is? I times? Yes. Okay, so the answer is R1 plus R2 times I test. Okay, that's actually not obvious, right? So there's like 3 rules that we kind of skipped to arrive to this equation. Right? Remember, everything is either an element rule or a voltage definition or a KCL or a KVL, right? There's nothing else. So let's break this down a little bit. So I test, if I label, so how we arrived to this, we said, I test, well, if there's some current I here, right, what is that current I with respect to I test? This current here, so there's some node here, let's call it U1, and I can call this 0. Right? What's the relationship of I to I test? By KCL, they're the same, right? So I can write this as, okay, I'll write it here. I equals I test. Right? Well, what current flows through R2? Same current I, right? So now I have the voltage across R2, let's call it V2, and voltage across R1, V1. So V1 is I times R1. That's just Ohm's law. I labeled it according to the passive sign convention, plus I times R2. So this now is KVL. I'm going from here, V2, V1, and I'm here. Right? So that's my V test. And now I just substitute. I test is the same as I, so then I test R2. And I get my first equation. Does that make sense? Okay. These are kind of shorter analysis because it's a simple circuit. So now R Thevenin equals V test over I test. And that equals R1 plus R2. So let's now formally define something. In series means that the same current flows through the elements. Right. So, what's the significance of this expression? Well, let's go back to our equivalent here and say what it is. This circuit is equivalent to something that has V Thevenin of 0, so I'm not even going to draw it, it's just a wire, and a single resistor of value R1 plus R2. So these two circuits are equivalent. So when you start getting piles of resistors in your circuit, if they're all in series, meaning they're all sharing the same current, you just go sum up all of these resistors and you represent them as one resistor. Yes?
Does I test not have to follow the passive sign convention?
Oh, the question was, does I test not have to follow the passive sign convention? Great question. And the answer is no, because V test is not really the voltage of this element. Right? I'm just defining V test this way to be able to measure what's going on with this element over here. Right? I could have gone and for this particular source labeled, I element however I want the direction and V element of that, and then I equate that to the V test. Here V test is just I really want it applied this way. Right? Okay, remember how we did, I guess, in this case. Remember how we did the I element, V element, right? I want to have this V element be V test and this I element be I test. So I need to obey that sign. Right? So it's passive sign convention for that circuit, not for the test source. Yes?
So what was our definition for
Our definition for dependent
dependent source?
source. Yeah, it was what I drew here, right? There is some control voltage or current in the circuit in one of the elements or between two nodes that defines the value of the source in that same circuit. Right? Just defines the value. Now, this is a battery whose value is alpha V1, VI. Right? So the voltage produced at the outputs of this is alpha times VI. Right? Or the current produced by this source is alpha times IJ, where IJ is some current somewhere in the circuit. Yeah. Okay. So, let's do another quick one. I think we have a couple of minutes. So, the point of this one was, after you see resistors like this that share the same current, you can always simplify them with an equivalent resistor. which is just the sum of the values, regardless of the actual size and physics involved with these resistors. This could be a narrow wire, huge wire, etc. You can intuit about that by understanding that a longer wire has more resistance. It shares the current, but that's sharing the geometry. Right? This is for any two arbitrary resistors. It's true. Right? So let's do another one. So this one, I want to do this circuit. So this is now I element. Yep. Right. And I want to create a Thevenin again. Okay? Step 1 is trivial. What is Thevenin? Again, no sources in the circuit. 0. Right, great. Step 2. Okay, I need to apply a test. Do I apply a test voltage or test current? Someone says current. Okay. Voltage. Okay. Can you speak up? Nice. Okay. So the comment was, hey, I remember what happened in an interesting circuit in the last lecture. And there, because there's two nodes, when we apply a test voltage across, like we applied in an interesting circuit, then each one, the current through each one of these branches or elements was independently set by just the voltage across. Because all of these elements share the same voltage. Right? This is one node, this is another node. Right? So no matter how many of these elements I keep adding, just like we kept adding strips to our touch screen, they all see the same supply. Right? Does that make sense? So the same deal here. That makes it a lot easier for me to compute what the current through each one of these elements is. So let's label these currents. This is I1, this is I2. So just like we did in the touch, what would I1 be in this case? V test over R1, right? And then I2 would be V test over R2. And then by KCL, what's the relationship of I test, I1, and I2? Equals what? Yes. I1 plus I2. And that is V test times 1 over R1 plus 1 over R2. Right. And so now I can find R Thevenin equals V test over I test. And that is 1 over R1 plus 1 over R2. And that I can figure, oops, I don't want that. I can redo this as this. Now, we're going to label this as R1 parallel R2. This is called a parallel operator. And again, we said that R1 and R2, this circuit is equivalent to a circuit that has R1 parallel R2, single resistor value. Does that make sense? Again, it's some resistor because our Thevenin voltage is equal to 0. So there's no source. So it just leaves the Thevenin resistor. And in this case, the Thevenin resistor is a product divided by a sum of the two resistors. And if I have more of them, as you'll see, you can easily derive, it just becomes a sum of 1 over these resistances, right? So if I have more resistors in parallel, you just keep applying this parallel operator. Okay, so just going to write this, what in parallel means. We're done. Means that voltage across them is the same. Okay? And now you see kind of why we applied V-test in this case and I-test in the previous case. Okay, we'll continue next lecture. Thanks. Hey. Okay.
This is for the homework problem.
Okay.
So I was wondering, for this problem,